Okay, the screen share looks fine. Everyone can see. Can the people in the back read the text from the screen? Okay, good. Let's see, we're just about ready to begin. Just to make sure everyone's in the right classroom, this is Chem 112, the first in the organic chemistry sequence. Has everyone received my introductory email with regards to the syllabus and the first note set? Anyone not received the email? If you're not on the wait list or trying to add the class, that's normal. I'll be collecting your emails at the end of this class session. Beyond that, if you could please raise your hand if you are enrolled in this course. If you do not have the note sets and you are enrolled in this course, please pick up a note set. The first lecture's note set will be provided to you. The rest you'll be responsible for printing out from the Canvas shell. So at this time, please come up and pick up the first note set so we can have a productive discussion today. Yes. Oh, okay. Please go right ahead.
This is same notes from the email, right?
Yes, yes. So if you have from Canvas or the email, they're both identical. Yes. Yes, it'll be posted sometime soon. Yeah. Okay. Who here is on the wait list? Let's see. Keep your hands up. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I have 6 students, correct? On the wait list. I have extra copies. Oh, okay. If you're on the wait list and do not have a copy, please raise your hand. Oh, I'm printing them out. Good, good. For those who are trying to add, if you do not have a copy, you're welcome to come pick one up. So please, at this time, please feel free to pick up a note set if you do not have one. Okay. Everyone has a note set? Okay, perfect. Really don't be shy to pick them up. I lecture off the note sets. Okay, so beyond that, before we get into the actual course, I just want to talk a little bit about the syllabus. And to do that, we'll just talk about it verbally. You can check it in the email as well. So the main things about this class, our lab meets twice a week. So lecture is 5:30 to 6:50, lab is 7 to 10. You're expected to attend all lecture and laboratory sessions. You'll have a quiz at the beginning of every lecture session worth approximately 3 to 5 points. So attendance really is necessary in order to cover the vast amount of material that we're going to approach in this course, and missing lecture or lab sessions, especially for the multi-day labs, really sets you up to have difficulty completing the lab reports and succeeding ultimately on the exams. So in terms of requirement, the required textbook is Organic Chemistry by McMurray. I have no preference for what edition you buy. You can buy an older edition as long as it's beyond the 5th edition. Think of the textbook for this class as a reference. If you happen to find an organic chemistry textbook that approaches concepts in a way that you find a little bit more comprehensible, you're welcome to use any organic chemistry textbook. I will assign homework from the McMurray, and I will specify the edition for the homework problem questions. Beyond that, you'll also need the microscale organic laboratory manual. This is available on reserve in our library. So if you're waiting to receive your textbook, go to the library, provide them the ISBN, and they will direct you to the location of the laboratory manual and the textbook. There's no reason while you're waiting for your book to arrive to not be prepared for the upcoming lab and lecture. Does that make sense to everyone? The library is the building. If you immediately exit and you just keep going in that direction, it's the largest building in the center of campus. Beyond that, you also need your lecture notes each class session. I lecture and I will be recording lectures using screen capture on each of these note sets. So if you happen to miss a lecture section, or more importantly, if you want to review a lecture concept or see how I explained a lecture concept, you're more than welcome to reference the recorded session, which I'll post on Canvas. Beyond that, the scientific calculator, the TI-30XA calculator, allow me to show it to you. So this calculator right here is the only one permitted for the final exam and on all exams. You will not need a calculator for the majority of the exam questions. In organic chemistry, it's primarily qualitative, but nonetheless, if you want to bring a calculator to the ACS, this is the only one we're permitted to allow students to use per ACS policy. Okay. Beyond that, the solution manual is available in the library, so you don't need to buy the solution manual. I would highly recommend, and I'll bring one next class session, to bring and buy a molecular model kit. I'll permit you to use a model kit on all of your exams, and it's really useful when we start to deal with geometric reasoning. Okay, beyond that, in terms of boilerplate class structure, we will have 3 exams, each worth 100 points, or 10% of your overall grade. Beyond that, there will be a 200-point final, and the final is split among 2 separate exams. The first of which is written by me, the second of which is the standardized American Chemical Society exam. Now, you may ask, why are we requiring you to take this exam? For the majority of you, once you transfer, you will end up at a college that will require you to verify your understanding of the material in organic chemistry. In many colleges, they require you to take the ACS and score above a certain percentile in order for these units to transfer. So it's really important that you not just focus on getting your desired grade in this class, but understanding the material, because when you transfer, in many cases, you'll be expected to demonstrate your knowledge of this material on an exam in order for the unit to successfully transfer. Does that make sense? You'll be taking the same exam in both places, so it's good practice. Okay, beyond that, speaking of exams, in order to receive a passing score in this course, anything above a D, you must score a minimum of 65% average on all of your exams, final, and quizzes. So I will add up all the points, and if you have at least 65%, then I will begin calculating your grade from there. Does that make sense? You must have at least a 65 average on all of your exams, quizzes, and final. Okay. So beyond that, the second major portion of this course, and the one that I view as highly important that you take seriously, are the lab reports. So labs are worth 20 points each, and unlike 101 and 102, I'd like you to think of these as not just experiments where you're analyzing your data and reporting your findings, but similar to that of an essay assignment. The writing requirements are a lot more comprehensive for the lab reports, and we'll talk about them in more detail in the laboratory, and we'll provide you some examples. Okay. In terms of, we'll talk more about lab-specific policy in laboratory. In terms of homework, you'll see homework posted on Canvas. It's worth 10% of your grade. All of the grades will be posted on Canvas. You can check your current score at any time on Canvas. And please check Canvas regularly. This is my primary method, which I provide announcements and provide materials for you. Okay. Outside of that, in terms of ad policies, for the first 2 weeks, I will be taking attendance every class session. If you happen to miss a class session and do not provide me with a written excuse for that absence or written notification that you will be absent, you may be dropped from this class in order to fill space. These classes are relatively high demand, and we want to make sure all the students who are enrolled in this class intend to take and complete the class. Additionally, if you intend to drop the class, please do not just disappear off the face of the earth. Please make sure to go through the formal drop process to ensure that at the end of the semester, there's no accidental F assigned because you weren't dropped. I'll be checking and taking attendance periodically throughout the semester, and students who are absent for more than 2 contiguous weeks will be dropped. Any questions on those policies? They're relatively standard from all courses. Okay, this is a big one, and I really do want to talk about this a little bit in detail. Academic honesty. So especially with regards to the lab reports, your lab reports will be handwritten, and they must be your own original work in terms of your explanation, the pros, and all of the components of your lab report. Labs are done individually, so it's highly unlikely that 2 students will have identical data sets. Likewise, for exams or any take-home components of any exams, quizzes, or other assessments, it must be your own original work. We are getting the stage. Organic is really the class where you're starting to receive your training to become a professional in your given field, be it biology or chemistry, and the skills and habits that we're aiming to develop in this class are reflective of the standards that we hold in industry and further graduate study. So please make sure, if I happen to observe a case of plagiarism, the assignment will receive an automatic 0, and further cases of plagiarism will be forwarded to the dean for appropriate arbitration. Okay. Beyond that, the Learning Resource Center, which is found in the library, is an excellent source of tutoring and potential help on homework, assignments, and other components of the course, such as laboratory reports. Many of the tutors found in the LRC have been trained and approved by the faculty here, and they're quite reliable. Additionally, we also have a mentorship program that meets Tuesdays from 6 to 10 p.m., where we have specifically trained organic tutors who are available to answer your questions. All of these are optional activities, but highly recommended in order to help you succeed in this course. Okay, beyond the boilerplate course objectives, I'd like you all, when you receive the syllabus, to look over the schedule that provides us the chapters that we're covering. The chapters in the book and the designations of the notes are a little bit different. I group a lot of chapters in the books together or take pieces from different book chapters in order to make a more cogent lecture. In general, if you have any questions on what section of the book you should be reading for a given lecture topic, don't be shy to ask. Beyond that, if we don't have any boilerplate questions on the syllabus, any other general questions before we get started? Yes?
Where is the mentoring on Tuesdays?
The mentorship program is in the, we'll announce the room on Canvas since we're still securing a room, and I'll let everyone know.
Thank you.
Okay. Any other questions before we get started? Just a side note to preface this before we begin organic chemistry and to give you a little bit of insight into who's teaching your class. I'm a trained organic chemist. I did research in synthesis, which is a subfield of organic chemistry. Organic chemistry really is probably the most useful chemistry course you take from the perspective of a biologist or a chemist, because it's really our way of understanding molecular structure and function in a very tangible way. For those who are going into med school, organic chemistry provides you a training in dealing with large amounts of data, which may be contradictory in nature, and using a series of rules and principles to arrive at a conclusion. It really focuses on the act of thinking through a problem and on qualitative reasoning. So, as such, we'll be looking at a lot of case studies in this course and dealing with systems using the principles that we cover in each chapter. Beyond that, organic chemistry really is the next chemistry class before you begin to move into the professional field. For those who are graduating with a bachelor's or transferring with the intent to graduate with a bachelor's degree, this really is about the most chemistry exposure you're going to get as a biologist, and it really serves as the basis in terms of chemical techniques in the handling and synthesis of organic molecules. So it's really a vital skill to learn and develop, as inherently when you're dealing with biology or chemistry, you will have to make things, you will have to process things, you will have to purify things, and you have to understand and reason through the behavior of compounds in biological systems and in chemical systems. So as this is a second year course, you'll be held to a higher standard in terms of the quality of your lab reports and in terms of the standards of participation and attendance for class sessions. I'd like you all to take this course seriously and make sure to put as much effort into preparing for each lecture as possible, as these lectures are quite dense, and the more material you've read beforehand will prepare you to succeed and engage in the lecture content. So ideally, you'll be reading through the chapters, looking over the notes ahead of time. And if you have any questions at all, I'm available via office hours. My office is in the lab room, 1207. I'll point it out to you when we reach the laboratory section. And I'm very available via email. Don't be shy to ask questions. I'm here to help you succeed in this class. but the standards are rigorous as this is your professional training in chemistry. Any other questions in this class before we begin? Everyone has the note sets, correct? If you don't have the note set, please come up and pick one up. Okay, so let's get started with today. So let me just clear this up. Okay, so let's get started. So this first chapter is going to be a mixture of review and new content, depending on the material covered in your 101 and 102 courses. Some material may feel new. All of this is ideally material that should have been covered in 101 and 102, and I'll note any new material as we progress through this class. So to set the stage for organic chemistry is a relatively old discipline of chemistry, as chemistry itself is quite an old discipline of study. All living things are composed of organic molecules, and organic compounds are the principal active agents of the majority of pharmaceutical agents. The majority of the medicines, drugs that we take and have developed are organic compounds. In the mid-1800s, the general field consensus was that organic compounds were difficult to isolate, difficult to purify, and difficult to prepare. It was thought at the time that organic compounds contained a quote-unquote vital force that made it such that they could not be prepared from readily available materials. However, in 1816, Chevreul showed that you could prepare soap from animal fat and alkali, which is sodium hydroxide. This is quite significant since, in effect, we are performing synthesis. So we are starting with a reactant organic starting material and generating new products. So this would be our reactant, and these would be our products. Okay, a slightly more significant development in this field of study was in 1828 when Wohler showed it was possible to convert an inorganic salt of ammonium cyanate into urea. For those of you who recognize this structure, urea is a principal biological product, and there have been efforts to isolate urea and purify urea from natural sources. Nonetheless, this was the first case where us as chemists had started with an organic, or in this case, an inorganic salt with organic functional groups and convert it into a new useful compound. So this is really the heart of synthesis, and this provoked a lot of additional study into the preparation of compounds and the study of organic compounds. So what exactly do I mean when I say an organic compound? Organic chemistry is the study fundamentally of carbon compounds. If we had to pick one element in the periodic table to signify the greatest importance, organic chemistry really focuses on carbon. 90% of 30 million compounds in our universe contain carbon. It's one of the more ubiquitous elements in terms of functional compounds. And carbon as a group 4A element prefers to form 4 bonds. So if we had to think of carbon, it typically likes to form 4 bonds. With what, you may say, and that's really the interesting part of organic chemistry. Depending on what functionalities we have bonded to carbon and how those functionalities are arranged, we get different properties, different reactivities, and different functional uses. So that's organic chemistry as a broader field. So now what we're going to do is we're going to review the fundamental components of atomic structure. Okay, so starting off, we're going to start with the basic premise that matter is composed of atoms, okay? And an atom, quite simply, is the smallest subunit of an element with the properties and reactivity of that element. So to give you an example of that, suppose we are looking at a cube of sodium. Suppose we were looking at a cube, in this case, of sodium. What are some properties of sodium? How does sodium react? What's a marquee property of sodium? If I put someone like, sure. What happens if I put straight elemental sodium into water? Yep. Yes, it generates hydrogen. So sodium, as one of its properties, it reacts with water. Okay, so if we look at this chunk of sodium and we decide to look at an individual atom of sodium, so let's suppose we look at an atom of sodium now. If we took that atom of sodium and we reacted it with a molecule of water, would we observe a similar pattern of reactivity between this bulk sodium and this atom? Yes, and that's a fundamental principle of an atom. It's the smallest subunit of an element with the properties and reactivity. Now, this is not to say that atoms cannot be divided into smaller fundamental particles, right? Atoms themselves are composed of 3 fundamental particles. And we'll be looking at these fundamental particles to help understand atomic structure and atomic properties. So the first of which is a proton. Protons are typically represented by P+, and protons are positively charged particles. Protons have a relatively large mass with a mass of 1 AMU. So if we wanted to draw a proton, we draw it as a circle with a plus inside, just to showcase they are the source of positive charge in an atom. Okay, now, using this idea of protons, we can develop a more useful definition of an element. We can also think of an element as a substance whose atoms all contain the identical number of protons. And one way that we express the number of protons is using the number called the atomic number Z. So the atomic number Z represents the number of protons. So all atoms of the same element have the same atomic number. Okay, now from this we can create a bit of a code here. And each element has a unique symbol with a unique atomic number. Okay, and if we're looking at the periodic table, the first thing that's always shown for a given element is the atomic number. So, for example, if you look at chlorine in the periodic table, the atomic number is shown right above the element symbol. So this is the atomic number. Would someone like to tell me what is the atomic number of chlorine in this case? 17. Yep. The atomic number is 17. So how many protons does chlorine have? 17. Yep, exactly. Okay, good. Perfect. So looking at the periodic table, you can clearly figure out the atomic number and the number of protons for a given element. Good. Now, moving on from here, we're going to look at our next fundamental particle, which is the neutron. Now, neutrons are abbreviated with the symbol N0. They're a neutral particle, so they have no charge. And the main feature of a neutron is they're a major source of an atom's mass. They have a mass of 1 AMU. We're always going to be mindful of atomic mass because it's very important for what are known as isotopes, which we'll talk about in a moment. As a general formula, we can express the total number of protons and neutrons for a given element using the mass number A. So the mass number of A is the protons. Let me use the appropriate color for that. Protons plus the neutrons. So let's use a different color for that. There we go. So the mass number represents the total number of particles with significant mass, or the total number of protons and neutrons in our given atom. Okay, so as I said, the mass number indicates the total number of protons and neutrons for an atom. The reason why we've decided to use this idea of mass numbers is that there are isotopes found commonly in nature. So what are an isotope? What are isotopes? So isotopes are atoms of the same element. So since they're the same element, what does that tell us about its properties? Since they're the same element, what do they have the same number of what? Same element, same number of protons, exactly. So They have the same atomic number and the same number of protons, but they have a different number of neutrons. Okay? And as a result, they have a different mass number. Now, a classic example of two isotopes, you don't typically see oxygen 18. It's quite expensive to generate and enrich. But because isotopes are of the same element, would you expect them to have similar properties and reactivity? Yes. The atoms of the same element have similar properties and reactivity. So we wouldn't expect oxygen 18 and oxygen 16 to behave substantially differently in terms of reactivity. There are subtle differences, but for the most part, they react and engage in chemical reactions in a similar manner. So, for example, if you had H2O18 and you compared it to H2O16, let's suppose that we decided to react them with a chunk of sodium. Would you expect a substantially different reaction to occur in both of these cases? No. They're compounds containing identical elements. The only difference being this oxygen has a slightly larger mass number, it's slightly heavier. That's not to say that these two isotopes have entirely identical physical properties, but for the most part, they react in similar fashions. Now, the last and probably the most important fundamental particle that we'll be dealing with this class session are our electrons. So, electrons fundamentally are abbreviated with an E minus. They are negatively charged particles with a mass of 10 to the negative 4th AMU. Electrons have a relatively small mass, but they are the primary component of negative charge in our atom. Now, the main way that we see electrons prop up and affect properties and reactivity are when we start looking at ions. So in the case of ions, we are dealing with the same element. So if we're dealing with the same element, we have the same number of protons. The main difference for ions is that we have different charges. And as a consequence, we have a different number of electrons. So ions, the only distinction between ions is that we have different numbers of electrons. So for example, if we look at O18 and O18 2 minus, where can we find the charge? Where is the charge located in an isotope symbol? Upper right-hand corner, right here. So this number in the upper right-hand corner represents the charge. And as we'll discuss in a moment, the charge is equal to the number of protons minus the number of electrons. Now, looking at O18 versus O18 2 minus, we see that the oxygen on the right, this ion, has a negative charge. We call ions with a negative charge an anion. It's a negatively charged ion. So looking at this formula in a little bit more detail here, what do we have an excess of in anions? Do we have more protons or electrons? Electrons. So anions, we have excess electrons. Okay. For our cations, so let's switch to a new color. In this case, we're looking at potassium plus, a typical metal cation. In this case, if we have a positive charge, do we have more protons or electrons? Protons. We have excess protons. Okay, perfect. So far, so good. Now, in order to calculate the actual number of electrons in a given chemical species or in a given ion, we can rearrange this equation just by moving the number of electrons to the left and the charge to the right. And we see the number of electrons is the number of protons minus the charge. Now, to show that this equation actually pans out here, let's take a look at O18 2 minus. Okay, so using this equation, how many protons do we have? How many protons does oxygen have? So this number up here is our mass number. And this number down here is going to be our atomic number. Okay, so with that information in mind, how many protons does oxygen have? 8. Yep. So our number of protons is equal to our atomic number, and it's 8. Okay? And what is our charge? Yep, our charge is -2. Okay, perfect. So plugging it into this equation, we see our number of electrons. Switch colors here. Our number of electrons is equal to our protons, 8, minus our charge, which is -2. Now, when we're subtracting a negative number, that's essentially adding a number, right? So how many total electrons would we have? 10. 8 plus 2 gives us 10 electrons. Does that make sense to everyone? So counting electrons is a really important skill that we'll be developing and continuing to use throughout this class. And it's really important that you're comfortable counting electrons for neutral species and for anions and cations. Now, let's delve into atomic notation and isotope notation in a little bit more detail. So let's take our typical framework of O18 over 8 2 minus. And first and foremost, the number in the bottom left-hand corner is our atomic number. So this is our atomic number, otherwise known as Z. As we've discussed previously, the number of protons is equal to the atomic number. Now, the number in the upper left-hand corner is our mass number. And the mass number represents the number of protons and the number of neutrons. Finally, in the upper right-hand corner, we have the charge. Now, which of these 3 symbols do we not always have to include? Are we being a little bit redundant when we give you the atomic symbol and the number? What did we discuss previously about the atomic number? Is it the same for a given element? Yes. So if I tell you it's oxygen, can you look up the atomic number? Yes. So in many cases, this atomic number is not provided. And you get the atomic number from the periodic table. So in this case, you'd look up oxygen, you'd find the atomic number above the oxygen symbol, and you'd see it has an atomic number of 8, so it has 8 protons. Does that make sense? Okay, so let's take this idea and let's try to apply it to a new system. So I'd like you all to take a moment and I'd like you to try and figure out the number of protons, neutrons, and electrons in iron 56 3+. If you need a reference, the periodic table is both provided in your notes and on the board. So let's take a moment, and you're welcome to communicate in groups. And I'd like you to figure out the number of protons, neutrons, and electrons in iron 56 3+. So the number in the upper left-hand corner is the mass. So it's, where do we get the protons from? Yep, and the number is 26 above. So everyone's going pretty quickly through this, so let's now come together to discuss this problem. So let me switch to the appropriate colored pen for this. Okay, so first and foremost, if you go and look at the periodic table and you find iron in the periodic table, what is the number, what is the atomic number from the periodic table for iron? 26, yep. Okay, so our number of protons, which is equal to the atomic number, is 26. Okay, so from this information, let's just fill that in our symbol, 26. We can now calculate the number of neutrons. So the number of neutrons are equal to the mass number minus the atomic number. So what is our mass number? Yep, our mass number is right here. So this is our mass number. So in this case, we're going to plug in 56 minus our atomic number, which we figured out was 26. And 56 minus 26 gives us a nice clean number of 30. Does that make sense to everyone? Okay, so for our number of electrons, we need the atomic number and the charge. Where is the charge? Yep, and what is the charge? Yep, plus 3. Okay, so from this information, oops, one moment. So from this information, all we have to do is plug in our atomic number, which is 26, and subtract the charge, which is positive 3. Since this is a cation, as we can see, we have less electrons than protons. Does that make sense? Okay. If you had to pick one skill to really focus on, you want to be really, really competent at calculating the number of electrons. Okay, so let's now talk a little bit about how these particles are arranged in our atoms. So in this case, we are going to start looking at the Rutherford model. So the Rutherford model has a bit of ambiguity associated with, and let's talk about the few basic premises. First, our protons and neutrons are found together in a mass at the center of the atom known as the nucleus. The nucleus contains the majority of an atom's mass and positive charge. Electrons are thought to surround the nucleus, and the majority of an atom is empty space. So you can think of the electron as a cloud surrounding our nucleus. Does anyone find a bit of an issue with this wording for our placement of the electrons? Do we have any idea exactly where our electrons are in this model? No. It's not very descriptive. And we're really interested in the electrons since they govern reactivity. So efforts were underway to develop a more descriptive model, and this leads us to the Schrodinger model. So quite simply, let's start with this idea that electrons are small subatomic particles. So we'll draw them like a little dot. So this is our little electron. Now, the Heisenberg uncertainty principle, in effect, tells us the exact position and energy of a subatomic particle cannot be simultaneously measured. So if we as chemists want to figure out exactly where our electrons are and exactly what their energies are, we're out of luck. We can't. There's a fundamental uncertainty in the position and energy. Now, additionally, subatomic particles exhibit wave and particle properties. So if we look at electron behavior, you can also look at it through like a double slit experiment, for example, you'll see that these small fundamental subatomic particles act a lot like waves under certain experimental conditions. Now, this is really the origin of the Schrodinger model and the wave function. So let's switch one moment. Okay, so the first fundamental premise in the Schrodinger model is we're going to describe electrons as standing waves. So our goal in this process is to write a function that describes electron energy and then solve for the energy of an electron. So let's delve into this into a little more detail and develop a bit more of a concrete explanation of this process. Okay, so the Schrodinger equation is best represented by the following equation. You don't have to worry too much about the specifics. We're going to really fixate on the results of the Schrodinger equation. So when we solve the Schrodinger equation, we get a series of what are known as wave functions. And these wave functions, which are represented by this symbol, essentially describe the wave nature of an electron. Relevant to us chemists is this wave function is dependent on 4 quantum numbers. We call them N, L, ML, and MS. And what we're going to look at is how these quantum numbers affect the region of space electrons occupy. Okay. So in effect, we can only really figure out or solve for the energy of an electron for a specific set of quantum numbers. So we are going to set, and we're going to look at a set of quantum numbers, and we're going to look at the wave function and the energy of an electron for that set of 4 quantum numbers. So from this idea, each unique electron, so each unique electron in a given atom has a unique set of quantum numbers. So we can think of these quantum numbers as like an ID tag for an electron. And we'll elaborate on this idea more once we start looking at orbital pictures. So up until this point, none of these numbers have actual physical meaning. None of these correspond to anything in our physical world. However, when we look at the wave function squared, this represents something that's quite significant for us chemists. It represents what's known as an orbital. And the best description I can give for you an orbital is the relative region of space an electron is likely to be if it has a given energy. So it's the probability distribution map of an electron of a given energy. So the best way I like to think about an orbital, it's a cloud of electron density for an electron of a specific energy. So the 2 main features of an orbital, we have a fixed energy and we have an uncertain position. For those of you who use Uber, for example, and you're waiting for your driver to pick you up, it shows you a general region where your driver is likely to be. It doesn't show you the exact location. You know our electron is somewhere in this region of space, and we know our electron in that region of space has a certain energy. Okay, so we've gotten a little bit closer to describing our electrons in a useful way. We now know the relative region of space an electron of a given energy is likely to be. And from this, we can start to see and start to describe electron interactions. Does that make sense? Okay. Now, as you see, different orbitals have different shapes. And we're going to talk a little bit about how orbital shape depends on these quantum numbers. Everyone okay so far? Okay. So we have these orbitals. And now let's talk a little bit about how these quantum numbers affect orbital size, shape, and energy. Okay. So depending on the exact orbital we are dealing with, set this up just right. Okay, good. So depending on the orbital, an electron is more likely to be in certain regions of space. So the first major quantum number we're dealing with is the principal quantum number. So the reason why the principal quantum number is so important is it dictates the orbital size and energy. So it controls how large our orbital is, how far away from the nucleus our electron is, and how high of an energy the electron has. So the energy of an electron is proportional to -1 over n squared. So as n increases, our energy increases. Now, would one of you like to volunteer and try and help us explain why do we have this negative sign? What is that negative sign trying to tell us about the relationship between an electron and the nucleus? What does that negative sign tell us? What does a negative energy tell us? Is it high in energy or low in energy, an electron associated with the nucleus? Yes? Yes, a negative number tells us the electron that is close to the nucleus is lower in energy. So as we increase our orbital size, as we get farther away from the nucleus, what happens to our energy? The number gets smaller, but the value becomes more positive. It's higher in energy. Think of it like this. So if we wanted to model energy, so n is equal to 1 is all the way down here, and n is equal to 2 is up here. If this is, for example, -100 compared to -50, sure, this -50 is a smaller absolute number, but which of these two energies is lower? Which of these two numbers is more negative? n equals 1. The electron closer to the nucleus is lower in energy. Does that make sense? Okay. So, the effect of changing n on orbital size and energy is quite pronounced. For example, looking at a 1s orbital, or n is equal to 1, compared to a 2s orbital, which is n is equal to 2. Which of these two orbitals is larger? N equals 2. You can visually see that the region of space the electron is likely to occupy gets larger, and the electron is farther from the nucleus. Now, this may seem a little bit esoteric. Let's now tie it back to the periodic table. So, electrons in atoms are found in principal energy levels, also called shells. We see shells in our periodic table by the row number. So you may notice in the periodic table that there are numbers next to each row. This row number represents n. So if we have this row number of 1, what is our n value for that shell? 1. This is n equals 1. If we're looking at the second row in the periodic table, what is our n value? 2. Exactly. So we can map and look at n, and we see that as we move down the periodic table, our n increases, so our overall element size also increases. Atomic radius. Now, a key feature of this idea of shells is that all orbitals with the same principal quantum number n are in the same shell. So for example, as we'll discuss in a moment, there are shells that contain two different types of orbitals, and we call these two different types of orbitals subshells. Just like we discussed before, if we're dealing with the first row, what is our n value? 1. If we're dealing with a second row, what's our n value? 2. Okay. Let's now talk a little bit about subshells, and this is when we start to see different orbital shapes. So we now are going to take our principal energy level n, and each principal energy level n is divided into what are known as subshells with different orbital shapes. And we designate different orbital shapes with the L value. Now, what does L represent? L is the angular momentum quantum number. And as we can see, as L changes, what happens to the orbitals? What changes about them? Their shape, exactly. L, the angular momentum quantum number, specifies orbital shape. So our S, P, D, and F orbitals all have different L values. We'll talk about this in detail in a moment. Looking at the periodic table, once again, a subshell is a section of a row in the periodic table. And let's really take this time to zoom in on the periodic table, and let's identify and label all of the major subshells that we're concerned with in this class. So first and foremost, the first two elements in any given row are what are known as the S subshell. This is also known as the L is, one moment. This is also known as the L equals 0 subshell. The next major region is this region of 6 elements shown here. This is known as the P block or P subshell that corresponds to L is equal to 1. Finally, as we've conspicuously overlooked our transition metal, the central 10 elements in the periodic table are known as the D block, or L is equal to 2. The F block consists of these elements down here, the lanthanides and actinides. We don't commonly see them in organic chemistry as their properties and reactivities are quite unique. Any questions on how we map the different subshells in the periodic table? Yes?
What's the L value for the F block?
Ah, yes. F block is L is equal to 3. Mm-hmm. Okay. So let's now take a look at each of these L values and each of these orbitals. We're going to get quite acquainted with each of these orbitals, as these are the principal ways that we're going to describe bonding or sharing of electrons between atoms. So first and the easiest to describe is our s orbital. So an s orbital corresponds to L is equal to 0. As we can see from their shape, they are spherically shaped and they have one orbital orientation. So let's talk a little bit about ML for a moment. So ML is equal to negative L to 0 to positive L. And it describes how many unique ways we can orient or place an orbital in space. In this case, if we want to count from negative L to 0 to positive L, do we have any L value other than 0 for our s orbital? What's the value? What's the L value for an s orbital? 0. So how many unique ML values can we have? Do we have any values other than 0? No. So the only ML values we have are just ML is equal to 0. The reason why we care so much about the number of unique orbital orientations is, as we can see, for each unique ML value, each unique ML value gives us a unique orbital. So as we can see, if we have one unique ML value, how many unique orbitals do we see for the S subshell? How many pictures do we see? 1. Because we have how many unique values? 1. Okay, let's keep going with this. So we're next going to have to discuss a unique behavior that occurs when we move further down the periodic table and our principal quantum number increases. So a node begins to appear. And as we look at the 2s orbital, we see the appearance of a region of space with no electron density. So a node is a region of space that has 0 electron density. We can calculate the number of nodes in an orbital So the number of nodes is equal to n minus L minus 1. So in this case, for a 2s orbital, let's take a moment and let's write down all of the quantum numbers that we know. So what's the n value for a 2s? 2, yep. So this is n is equal to 2. What's the L value? 0, yep. Okay, so looking at our number of nodes, we have 2 minus 0 minus 1, and we calculate that we would have a total of 1 node. Does that match our observed result? Yeah. So the reason why nodes are quite significant, they're regions of space with 0 electron density. And as we'll see when we discuss more complicated orbital pictures, nodes have a dramatic effect on orbital energy and orbital properties. Okay, let's now move on to our next orbital type. The next orbital type, as we can see, are p orbitals. These correspond to L is equal to 1. Let's switch to a new color to describe the p orbitals. Now, immediately looking at this orbital picture, do we see a region with no electron density? Do we see a node in these p orbital pictures? Yes, right at the center. So this region right here in the center is a node. Also right here and also right here. So always important to keep in mind. The next major feature, what are they shaped like? Hourglass, dumbbell, balloon, however you want to think about it. The main feature of a p orbital is that they're also symmetrical. What else do we notice that's unique about a p orbital? In this case, since we have L is equal to 1, how many ML values, how many unique ML values can we have? If ML goes all the way from negative L to 0 to positive L, let's write out all of our ML values. Let's write out all of our unique orientations. So if we have L is equal to 1, what number can we write? Negative 1, yep. 0 is a freebie. And finally, positive 1. As a consequence of this, how many unique ML values do we see? How many unique orbitals do we see? 3, yeah. So the number of unique ML values, we have 3 unique ML values. So as a result, we see we have 3 unique orbitals for the p subshell. Does that make sense? How the quantum numbers determine the number, shape, size, and orientation of each of these orbitals in each subshell. Okay, let's keep going and let's now briefly touch on the d orbitals. So the d orbitals, as we can see, have a quite unique array of shapes. The d orbitals, switching the color of my pen so that way we have a bit of change. The d orbitals correspond to L is equal to 2. Let's now take a moment and list all of our possible ML values. So what would we start off when we're listing ML values? Negative 2, yep. Yep, then negative 1. 0 is a freebie. Would someone else like to provide us the last 2? 1 and 2, yep. Positive 1 and positive 2. So how many unique ML values do we have? 5. And how many unique orbitals do we see in this subshell? 5. Okay, as a side note, do we see a node in this case? Yes. How many nodes do we see? So looking at this, let's take our node calculation. So our number of nodes is equal to n minus L minus 1. Let's suppose in this case we're looking at 3D orbitals. So we'd have 3. Oh, take a moment, one moment. let's look at the 4D orbitals. They're a little more interesting. Erase this. Yep. So 4 minus 2 minus 1, and that gives us 1 node. Depending on the exact n value, you'll see a different number of nodes. As you can see, there are a series of nodal planes with no electron density. Anytime you don't see a region of space occupied by an orbital, those are described as nodal planes. Not too important, we don't deal with a ton of d orbitals in this class. What is very important and is often overlooked when discussing orbitals has to do with orbital phase. Now, recall, how did we make these orbital pictures? What did we describe electrons as? What was that? Clouds, sure, but what was that interpretation based on? These small subatomic particles don't just have particle properties, they also have wave properties, exactly. Now, as a consequence of that, waves are phased. So they contain regions of positive and negative amplitude separated by a node. So here's our node in our theoretical wave, right? And we have regions of positive amplitude and negative amplitude, right? So since we described and we model electrons and we generated these orbitals using a wave interpretation, the majority of the orbitals that we draw, especially the p orbitals, have this wave-like phasing. We have a region of positive amplitude, a region of negative amplitude, and those regions are separated by what? A node. That's why we have a node in the center of our p orbital. So this is our node. Now, this plus and minus is not describing charge, it's describing amplitude. And this affects how orbitals interact and overlap. Okay, so this is not a positive charge and negative charge, this is amplitude. And we'll talk a little bit more about what that means when we discuss bonding. Does that make sense? I just always want you to get in the habit of drawing your p orbitals with phasing, as that's a central thing that we'll need for later chapters in organic. Okay, let's keep going. Any questions so far? Any questions so far? This looks like review from 101, Chem 101, right? Does this look familiar to everyone? Okay. So, we're now going to discuss electron configurations. This is where we start filling orbitals with electrons. So we're going to take these orbitals, which we're going to describe as buckets, and we're going to fill them with electrons and look at the energy of electrons in each of these orbitals. So a central premise is the Pauli exclusion principle, which quite simply says no two electrons in the same atom can have identical values for all 4 quantum numbers. So just as a refresher, n is the principal quantum number indicating the energy and size of an orbital. L is the angular momentum quantum number, specifies orbital shape. ML is described as the magnetic quantum number, specifies the orbital orientation. Now, the reason why I've grouped all of these quantum numbers together is these 3 quantum numbers can best be described as looking at the orbital. The last quantum number describes the exact electron in a given orbital. So the last major quantum number to discuss focuses heavily on the properties of an electron. And this last quantum number is known as ms, or the spin quantum number, and it specifies electron spin. Ms can be either +1/2, otherwise known as up spin, or -1/2, otherwise known as down spin. So there are only two possible values for the spin quantum number. Now, unfortunately, the spin quantum number has a bit of a misleading name. The spin quantum number is really describing the direction of the electron's magnetic moment. And the reason why it's called spin is if a particle is spinning, it generates an electric field. Now, electrons obviously aren't just spinning in circles in an atom, but they generate a magnetic field, and this ms value indicates the direction and orientation of that field. Does that make sense? Okay. Now, a key feature of the spin quantum number is that opposite spins will pair in an orbit. So if we have these two electrons of opposite spin, so this is ms of +1/2, and this is ms of -1/2, these two electrons will spin pair in an orbit. So this box is going to be describing our orbital. This up arrow describes an ms of +1/2, and this down arrow describes an ms of -1/2. So if we can only have two given values of ms for a given orbital, which has an n, l, and ml value that's fixed, how many unique sets of quantum numbers can we generate? How many unique sets for a given orbital? 2. We can have a maximum of 2 electrons per orbital. You can have the n, l, ml +1/2, and you can have the n, l, ml -1/2. And if we try to put another +1/2, would we be describing a new unique electron? If we have the same set of quantum numbers, are we truly describing a different electron? No. So no matter how much we try, we can only fit a maximum of 2 electrons in an orbital, 2 unique sets of quantum numbers per orbital. Okay, so the key takeaway I want you to derive from this discussion: each orbital can hold a maximum of 2 electrons of opposite spins. So 2 electrons per orbital. Okay, now we're going to use this, and we're going to talk a little bit about how orbitals are arranged by energy. We are going to not go into too much detail into how we generate this orbital energy arrangement. Please consult your 101 notes, or if you'd like some supplemental reading, I'm more than willing to provide it to you. But for organic chemistry, we're just going to look at the orbital sorted by energy and talk a little bit about how we fill in these orbital energy diagrams. Okay, so this diagram is sorting each of our orbitals by n and l. So for example, a 1s orbital corresponds to n equals 1, l equals 0. The 2s orbital corresponds to n equals 2, l equals 0. What does the 2p orbital correspond to? What n value? Yep, n equals 2. And what L value do we have? What was that? 1. Yep. Okay. So as a general trend, what do we notice happens as we increase n? Does our energy go up or down? Up, right? Orbital energy increases as n increases. What about for L? As we increase L, what happens to our orbital energy? Does it go up or down? Up, exactly. The energy in general increases as you increase n and l, as you increase orbital size, and as you change orbital shape. Does that make sense so far? Okay. We can summarize this overall orbital energy diagram into a general filling order. So this is a general filling order. We'll come back to this when we start talking about electron configurations. So our next order of business is to figure out how many electrons in a subshell. So our goal is to figure out for a given subshell, for a given L value, how many electrons do we have? And, well, how many electrons can we fit in an orbital? Two, right? We can fit 2 electrons per orbital. So all we need to do is figure out the number of orbitals for that L value. So the reason why I have this picture is it shows us exactly how many orbitals for a given L value. So for L equals 0, for our s orbitals, how many orbitals, as we discussed previously, do we have? 1, right? We see 1 blank space for our 1s orbital. We have 1 unique orbital. So then, for our s subshell, we have 1 orbital times 2 electrons per orbital. That gives us 2 electrons per s block. Okay, so let's repeat this process for our p orbitals. So for L equals 1, as we discussed previously, how many unique orbitals do we have? How many, as we look at this picture, how many unique p orbitals do we see? 3, So we have 3 orbitals times 2 electrons per orbital gives us 6 electrons for the p block. Okay. Continuing on with this idea, let's now look at the d orbitals. So how many unique d orbitals do we have? So looking at the d block here, this corresponds to L is equal to 2. How many unique orbitals do we see? 5. Yep. Since we have 5 unique orbitals, 5 times 2 gives us 10 electrons per d block. Okay. An additional feature that I'd like us all to appreciate is this idea of degenerate orbitals. So orbitals with the same n and L value are degenerate. Now, what does that word mean in the context of chemistry? It means that they have the same energy. So, for example, if we look at our 2p orbitals, and we look at them on this orbital energy diagram, do each of these 2p orbitals, do each of these 3 2p orbitals have the same or different energy? Same. They're the same relative height in this energy diagram. They have the same energy. So we have the same N and L, and as a result, they have the same energy. Okay. Okay, now that we've established each of these rules for the maximum amount of electrons for a given subshell, we're now going to talk a little bit about the process of writing out electron configuration. So, first and foremost, when writing an electron configuration, we first need to count our electrons. So, in terms of counting electrons, we can figure out the number of electrons by taking the atomic number minus the charge. This is reviewed from our first discussion of isotope notation. Now, we're going to place electrons in orbitals from the lowest to highest energy orbital until all of our electrons have been placed. So what we're going to do is we're going to take this general orbital energy diagram and we're going to fill it with electrons from our given element. So to show how this works, I'll show a representative example and then you'll handle an example as well. So let's start with beryllium. So if we look up beryllium in the periodic table, what is beryllium's atomic number? The periodic table is both on the board and in your notes. Yep, so beryllium's atomic number is 4. So in this case, our number of electrons is equal to 4 minus 0, so we have 4 electrons to work with. Now we're going to generate, and we're just going to replicate our baseline orbital energy diagram. So we have the 1s, the 2s, and then our 2p orbitals. Okay, now that we have our orbital energy diagram all set, we're now going to fill this orbital energy diagram with our electrons. So what orbital do we start filling first? 1s. It's the lowest in energy. And how many electrons can we put in the 1s? 2. Yep. Okay, we've used up 2 of our electrons. Where do we put our next 2? 2s. So we fill it with 2 electrons. And we've used up all 4 of our electrons, so we're done. This is a complete orbital energy diagram. Does that make sense? Okay. Now, what we're going to do for electron configurations is we're going to take our orbital energy diagram, and the trick is you note the number of electrons in a given orbital n and L value. So the total number of electrons in degenerate orbitals. And for an electron configuration, you list the subshells, so the n and L values that contain electrons, and you indicate the number of electrons in that subshell with a superscript. So this is a bit of a wordy explanation. It's easier seen in practice. So looking at hydrogen, for example, what orbitals for hydrogen contain electrons? 1s. Okay, so we're going to write the 1s orbital. Okay, and how many electrons, how many arrows do we see in our 1s orbital? 1. So we're going to put a superscript of 1. So that's the configuration for hydrogen. Does that make sense? We indicate the orbital n and L value, and we indicate the number of electrons with a superscript. Okay, let's try a bit more of a interesting method of writing electron configurations. Let's take a look at the periodic table with this idea of subshells. So the periodic table itself is divided into regions of 2, 6, 10, and 14 columns. Now, why are these numbers so significant? Well, if we look at the left-hand side of the periodic table, we see a region containing 2 elements in each row. How many electrons total can we fit in an s orbital? 2. This is why this is called the s block, because the s block can accommodate a total of 2 electrons. By the same note, we see a region on the right-hand side of the periodic table. We see a region on the right-hand side of the periodic table that contains a total of 6 elements. How many total electrons can we fit in a p block? 6. Yeah. So this region of 6 elements is the p block. These are the elements in which you are filling the p orbitals. And the reason why we have a maximum of 6 in the p block is the p orbitals hold a maximum of 6 electrons. Continuing on with this trend, let's continue on and let's talk about the D block next. So this region for the transition metals in the middle of the periodic table that contains exactly 10 elements. What orbital are we filling in this case? D. And when we fill the d orbital, it can accommodate a maximum of 10 electrons. So there are 10 elements in the d block. And the p block is 6 electrons. Now, as additional interest to us, each row in the periodic table represents an energy level, or a region with or a shell, or a region with a unique principal quantum number. So the period number describes the outermost s or p orbital n value. So for example, let's just use an example to help clarify this. Suppose we're looking at an element right here. Suppose we're looking at this element here, and that would correspond to 3. That would correspond to argon. So what row in the periodic table is argon? What is the N value? 3. Yeah. So argon corresponds to N is equal to 3. So what is the N value of its outermost orbital, of its furthest filled orbital? 3. Yep. What block does argon lie in? Yep. The P block, more specifically, the P block for what orbital? 3p. Yep. So notice the row number corresponds to the N value of the outermost S or P orbital. This will be useful to help shortcut in writing electron configurations. Now, in general, we fill orbitals from lowest to highest energy. One moment. And we can summarize our orbital energy diagram into this general filling order. Now, if we're looking at each of the element boxes in the periodic table, each box in the periodic table represents room for a single electron. So if we start all the way at the top of our periodic table, each time we move a step in the periodic table, what have we gained when we move a step in the periodic table? Or let me showcase this a little bit better. So let's say we're going from here to here. We're moving one step to the right. What have we gained? 1 electron. Each step to the right in the periodic table is a gain of 1 electron. So we have gained 1 electron. So in effect, if you want to just use the periodic table to write electron configurations, you start at the top, and each time you move to the right in the periodic table, you add an electron to your current orbital. I personally don't prefer this method, but I always like talking about it since some students find it quite useful. So let's take an example and let's take a look at aluminum. So aluminum. First and foremost, we need to figure out how many electrons we're dealing with. So what's the atomic number of aluminum? So yep, the atomic number of aluminum is 13. So how many electrons are we working with? 13. So using our general orbital filling order, so 1s, 2s, 2p, 3s, 3p, 4s, 3d, where do we start placing our electrons? 1s. So we're going to take our 1s, and how many electrons maximum can we place in a 1s orbital? 2. S orbitals can hold a maximum of 2. What's the next highest energy orbital? 2s. So we still have electrons to spare, so we're going to take our 2s orbital, and how many electrons can it accommodate? 2. What's the next highest energy orbital? Yep. And how many electrons can the p orbitals in total accommodate? 6. Okay. The next highest energy, going through our general filling order, is the 3s. And how many electrons can the 3s accommodate? 2. Okay, let's take a look at how many electrons we've used up. 2, 4, 10, 12. Okay, so we've used up 12 electrons so far. So for our 3p orbital, how many electrons do we have left? 1. Okay. So this is a complete longhand electron configuration for aluminum. You're more than welcome to generate an orbital box diagram and then fill it using the method discussed earlier. Everyone okay so far? Let's check our time. We're out of time for today, but we'll continue on with this next class session.